All right, so the plan for today is to finish up one last little problem in section 3.3, subtracting integers, and then start working our way through 3.4 and 3.5, multiplying and dividing integers, and solving equations using integers, particularly looking at the division property. We talked about the solving equations using the addition subtraction property previously, looking at a new property to help us solve some different types of equations. Just a reminder, Unit 1 exam is this week. The material is sections 1.1 to 3.2 on adding integers, so the material that we had completely finished up last week. And sorry, my allergies are really bugging me this morning, so sorry if I'm rubbing my nose or my eyes as we go through class today. The sample exam was posted last week, so that should give you a pretty good idea of the length of the exam, the content that'll be on the exam. Again, I kind of recommend that you, when you feel prepared for the exam, you sit down at the sample exam, time yourself, uh, put yourself in the kind of same situation that you'll be in the actual exam, and take the sample exam as though it were the actual exam, submit it when the time's up, and then see how you did. If you felt comfortable with the sample exam, if everything seemed to go pretty well, then you're probably prepared for the actual exam. If maybe things took, oh, the sample exam came down. Let me pull that up really quick and check that. Um, I do have WebAssign up right now. Let me just double check. I thought it was not set to be due until this coming Sunday. Yeah, I think, yeah, it's looking to me like the sample exam, sample unit 1 exam is available Monday the 19th, Monday, August 19th. So like basically beginning of the course through Sunday, September 29th. So I think it should still be visible. The unit 1 exam came available yesterday morning at 9 a.m. So so I think the sample exam should still be up there. If you're not seeing that, can you send me like a screenshot or something of what you're seeing? But it should still be up there. It might be, you might have to like expand the window with the assignments or something to see it. It might have, come off of the bottom for some reason, like been pushed down a little bit, or maybe when the actual exam was posted, maybe it kind of moved the location of the sample exam a little bit. Um, but you should be able to still see the sample exam, I think, at least from what it looks like from my end. But again, if you're not able to, please either take a picture or a screenshot and shoot me an email, and I can try to figure out what's going on there. Um, yeah, but so I'd recommend taking the sample exam as though it's the actual exam. And if you know come across a problem, if you say, um, maybe there was a topic you thought you knew pretty well, but on the sample exam, you really struggled with those problems, maybe go back and review that topic, right? That might make your study time a little more high yield, where you can study the material that you really need to study and direct more time at that material and not direct time at material that you're already, confident on. Just a reminder, no Proctor U for this first exam. Couple little tech issues that popped up, and uh, I'm certainly planning to have that up and running for the second exam. Anytime that we're introducing like new tech, like I said, we're switching from Examity to Proctor U this semester. It's always, a little bit, there's always a little bit of tech issues to work out. So we're working on those behind the scenes, and that should be up and running for exam 2, exam 3, and the final exam. And as I mentioned a couple of times already, don't wait until the last minute to, okay, great. So you're able to find it. Yeah, so I think the sample exam still is up. So good to know. Uh, with these online systems, there always is a chance that, a date was marked, was set wrong or something like that, or a setting was set wrong. And sometimes they do things that I didn't expect. So, um, okay, so yeah, don't wait until the last minute to take the exam. My recommendation would be to plan to take it on or before Thursday night. Um, and that way, if anything were to go wrong, you have a full business day buffer as well as the weekend to get anything worked out. There are no extensions on the due date for the exam, so make sure that you give yourself enough of a buffer that if something happens, a power outage or a personal issue comes up or something, you have some time to work that out. Or if it's a tech issue, you have time to get in touch with me or to contact um, WebAssign support or CCAC's IT or whoever it may be to get that all sorted out before the due date on Sunday night. Okay, so any questions on anything from last time, anything about the exam, anything like that? All right. And whoops, this should be 3, 3, subtract integers. So one last problem in subtracting integers. So quickly recall modeling integer addition and subtraction. We can kind of think of this in maybe two different ways. We can think of it as kind of a vector quantity, a quantity with both size and direction, an integer number. And we can think of addition and subtraction as like saying move forward and move backward. And the positive negative sign of the thing we're adding or subtracting is telling us which direction to face, to the right or to the left. We could also model with colored blocks or counters and this idea of a neutral pair. So we can think of the positive negative sign being, say, a green versus a red circle or a counter or a block. A neutral pair being a combination of two green and red circles. So I can put in an additional two circles as long as one's green and one is red. They kind of are neutral. Or if I have one green and one red in existence in my problem, I can kind of cancel them out and get rid of them. And I'm thinking of addition and subtraction as meaning either add more or take away. So I might want to, for instance, add more red circles, or in another context, maybe take away some green circles, so I can combine these in different ways. Okay, so our last example here. Renee is on an alpine hike. The temperature is -7 degrees. Renee's sleeping bag is rated, quote, comfortable to -20 degrees. I don't know anyone who would be comfortable in -20 degrees in anything aside from being inside a house, but how much can the temperature change before it's too cold for Renee's sleeping bag? Now, one thing that makes this kind of difficult is that the numbers are negative, right? I have an outside temperature that's -7 and a sleeping bag that's rated comfortable to -20 degrees. So one thing, if you see the strategy for this problem right away, great, go for it. But one thing that we can do when we have a problem that's maybe a little more challenging like this, we have negative numbers, we're not really sure, whether we want to add or subtract them. Well, we probably know we want to subtract them because we're in section 3.3, but just looking at it, we might not be 100% sure what to do with these numbers, or if we're subtracting them, which one comes first. Would I want to do -20 minus -7 or the other way around? Maybe I'm not really sure. And it's a little hard for me to get a gut feeling because these are negative numbers, just a little less used to dealing with them. So maybe what I'll do is I'll kind of come off to the side here and I'll set up like a similar problem that's with kind of the same setup, but use positive numbers instead. So the temperature is, say, 50 degrees outside, and the sleeping bag is comfortable to, let's say, maybe 30 degrees. Right, so I'm just coming up with a sample problem that's a little bit easier. It's the same structure of the problem, but the numbers just aren't as bad to work with, and I can kind of get a gut feeling for what's happening over here. I can maybe get an idea what the solution method is going to look like on this slightly simpler problem, and then take that same method and apply it to the more complicated problem with the negative numbers. So this is a good practical test-taking strategy or problem-solving strategy. If you are stuck with the problem as it is, can you make it a little bit simpler? Now, if you make it way too simple, like the temperature is 50 degrees, the sleeping bag's rated at 50 degrees, well, it can't get any colder. Like if you make it way too simple, then you can't really apply that same method to the original problem. But this seems like it's kind of in the same ballpark. the sleeping bag's rating is colder than it is out right now. Negative 20 degrees is less than negative 7 degrees. So I kind of intuitively understand that it can get 20 degrees colder. It can change by negative 20 degrees. That's the change in temperature before we get to a temperature that is too cold for the sleeping bag. And I get that by doing 30 minus 50, by doing the sleeping bag's rating minus the temperature. 30 minus 50 is negative 20. I might have instead thought, should I do 50 minus 30? Right? Should I do the temperature minus the sleeping bag? But that would give me positive 20. But that's not the answer that I know that I'm looking for. I know that I want to say that the temperature could decrease by 20 degrees before it gets too cold for the sleeping bag. So I want to do sleeping bags kind of comfortable temperature minus the current outdoor temperature. That'll tell me the change in temperature before my sleeping bag is not rated for that temperature. So over here, my sleeping bag is negative 20. I didn't intend for the answer to be negative 20 and negative 20. That was just coincidence with the numbers I chose over here, 50 and 30. So I do sleeping bag's temperature minus the current outside temperature. And that's the answer to the problem. So I do the same method as over here, sleeping bag rated temperature minus current temperature. And again, here I can think of subtracting a negative number as adding a number. Negative 20 plus 7. I can think in terms of counters, or I could think in terms of the real line moving back and forth. I could also make this, say, 7 minus 20. But I see that I'm now thinking of adding two numbers together, two integers together. The integer that is the bigger size, that's the largest in absolute value, is the negative 20. So my answer is going to have a negative sign. And it's going to have size 20 minus 7. How much can the temperature change before it's too cold for Renee's sleeping bag? The temperature can go down 13 degrees. It can change negative 13 degrees before it's too cold for the sleeping bag. And that does make sense. Temperature is currently negative 7. If it got a little bit colder, it'd be like negative 8, then negative 9, negative 10, a bit colder still, down to negative 20. So it could go down 13 more degrees and still be within the rating for Renee's sleeping bag. Okay. Any questions on any of this? Now, one little detail that I want to mention here is the wording of the question. How much can the temperature change before it's too cold for a sleeping bag? It can change by negative 13 degrees. Now, note that if we said something like, how much can the temperature decrease before it's too cold for a sleeping bag? Well, we wouldn't want to say it could decrease by negative 13 degrees. We would want to say it can decrease by 13 degrees. This negative is kind of representing that decrease. So the decrease would be 13 degrees, or the change would be negative 13 degrees. We have to be a little bit careful, right? The same way that, like, I could say my bank balance went down by $13, or I could say, like, I withdrew $13 from my bank account. I wouldn't say I withdrew negative $13 from my bank account, or I wouldn't say my bank account went down negative $13. But if I asked what was the change in your bank account balance, you could say negative $13 would be the change in the balance. So be a little bit careful with the wording of the question. Any questions on anything up to 3, 3? Okay, then jumping into 3, 4, we did addition and subtraction of integers. And we had some of these ideas again of counters that could be green or red now, with red counters representing negative numbers. We had ideas of number line and kind of facing a certain direction as well as moving forwards or backwards. What if we want to model integer multiplication? If I have the product of a and b where a and b are integers, if I have a times b, what I mean by this is I want to add a b times. In other words, I want to do a plus a plus a, etc. b times. Now, it's not a big deal if you wrote b plus b plus b and did that a times. We know the multiplication is commutative, so we can really think of this either way, but this is the way that we'll choose to think of it. We're adding a b times. So we can model this in terms of our kind of vector quantity idea, the idea that if I'm, you know, if I'm doing, say, 3 times 4, I could think of adding 3 or going to the right 3. 1, 2, 3. Oh, didn't leave myself enough room. 4 times. So once, twice, 3 times, 4 times. I walked to the right 3. I added 3. And I did that 4 times. I could alternatively think of, for instance, doing -3 times 4. Adding a -3 is like subtracting 3, or in this case, I would just be doing -3 once, -3 twice, bringing me down to -6, -3 a third time, down to -9, and subtracting 3 a fourth time to -12. Okay. We could also think of modeling with, again, colored blocks or counters, where multiplication means something like duplicate. I could think of having, I guess I used green up here for the negative. I didn't intend to imply green associating with negative, just was using a different color. But I could think of 3 times 4, like if I have 3 green counters, and then I want to duplicate them 4 times. There's a second, a third, and a fourth row of 3 green counters. This gives me a total of 12 green counters. Or if I had -3 times 4, I want to take 3 red counters and duplicate them 4 times. There's a second, a third, and a fourth set of 3 red counters. Or this is just 12 counters of what type, of the red type. So we call those negative. Okay, so let's model 2 times 3 with various different signs. And in both of these different ways. So for 2 times 3, I want to add 2 3 times. So there's 1, there's 2, there's 3, and this takes me to 6. So starting out pretty simple here. Or I want two counters, two green counters, duplicated 3 times. There's a second set of two green counters and a third set of two green counters. Overall, I have 6 counters of what type of green, so I leave it as a positive number. So that's 2 times 3. Let me actually switch these two around. Had those in the wrong order. Okay, so negative 2 times 3. Let's look at that. So now I want to add negative 2 to itself 3 times. There's once going in the left direction. There's twice. And 3 times. So negative 2 times 3 is negative 6. Right? Because this is like negative 2 plus negative 2 plus negative 2. So I'm kind of like facing left and then moving forward in that direction 2 units. And I'm doing that 3 times. Or I could think of negative 2 times 3 as like having 2 red counters and like 3 sets of those, 3 like duplications of that. There's a second and a third group of 2 red counters. Overall, I have 6 counters of what type of red counters, so that represents a negative 6. So say negative 2 times 3 is negative 6. Now, what if I had something like, I don't want to, maybe I'll use blue. I don't want any connotation coming along with this. What if I had something like 2 times negative 3? So I want to add 2 to itself negative 3 times. What does that mean? It kind of means that I want to take away 2. So this means like take away 2 green counters 3 times. So instead of adding 2 3 times, I want to like subtract or take away 2 3 times. I want to take away 2 green counters, 2 green 3 times. I don't have any greens to start with now. I just have like nothing here. I would like to have 2 greens to take away so that I can do this once, but I can get more greens by adding in neutral pairs. So now I have enough greens to take away 2 1 time. I now have enough greens to take away 2 greens 2 times. And I now have enough greens to take away 2 greens 3 times. I can come in and take these away. They just go away. If I take away 2 greens 3 times, what am I left with? I'm left with 6 counters of what type? Of the red type, or that represents negative 6. So I actually see that if I do negative 2 times 3, I get negative 6, but also 2 times negative 3 also gives me negative 6. So what is this kind of saying over here? It's kind of saying I want to take away, I want to walk backwards in the positive direction while I'm facing the positive direction. I want to walk backwards 2 units 3 times. So So here's 0, -2, -4, -6. There's our -6. So whether I face to the left and walk forwards, whether I add walking forwards a negative number facing to the left, or whether I subtract, take away a positive number, whether I face to the right and walk backwards or face to the left and walk forwards, I end up moving the same direction. Or whether I directly add red counters, or whether I add a bunch of neutral pairs and then get rid of the associated green counters, I end up with the same number of red counters. Okay, so what about -2 times -3 now? When I had 2 times -3, what did I do? I said I take away 2 3 times. When I have -2 times -3, I want to take away, well, I want to take away what? -2 3 times. So this negative converted the add into the terms take away. And this -2 is the thing that we're taking away, right? This negative made a take away, and this +2 was what we took away. All right, so if I want to take away -2 3 times, I want to get rid of 2 reds, and I want to do that 3 times. I don't have anything to start with. So I'd like to take away 2 reds, so I put in 2 neutral pairs, and this gives me 2 reds, so I can take away -2 1 time now. I need some more. I can take away -2, or I can take away 2 reds 2 times now. And with a couple more, I can take away -2. I can take away 2 reds 3 times. Oh, didn't switch. This leaves me with 6 counters, but of the green type. Because I took away the reds, this leaves me with 6 greens, or just +6. Or in the number line, this is a little bit like saying, well, I want to take away -2, so I want to face to the left, but I want to take away, so I want to move backwards. I want to face to the left and then move backwards 2 units 3 times, bringing me to +6. So one thing that I notice is that if I multiply a positive number by a positive number, that gives me a positive number. Of course, I started with some amount of green counters and I duplicate them a bunch. I just end up with a bunch of green counters. But actually, a negative times a negative gives me a positive. Why is that? Well, I start with a bunch of neutral pairs. Well, I guess I start with nothing and I add in a bunch of neutral pairs and I get rid of a bunch of reds. I take away a bunch of negatives. Taking away a bunch of negatives, getting rid of a bunch of reds, leaves me left over with a bunch of greens now. Leaves me with a bunch of positives. On the other hand, if I have mixed signs, if I have a negative times a positive or a positive times a negative, I can either think of that as directly just starting out with some reds and duplicating them and ending up with a bunch of reds, or putting in a bunch of neutral pairs and taking away the greens, getting rid of the greens, leaving me again with a bunch of reds. So again, as usual, this modeling is helpful to understand the idea and see, like, maybe intuitively, why does negative times negative equals positive, things like that. But we certainly wouldn't want to multiply big numbers, big integers like this. So we have a rule. The product of 2 integers with the same sign is positive, and the product of 2 integers with different signs is negative. So if we want to multiply 2 integers together, the sign of the answer is either positive or negative according to this rule. And the size of the answer is just the product of the two numbers taken as if they were whole numbers, basically the product of the absolute values of the numbers. It is important here to note that the relative size of the numbers in multiplication does not matter. So if I have like 1,000,000 times -2, that's -2,000,000. It's not like, oh, well, the million is bigger, so the answer is positive or something. If it was 1,000,000 subtract 2, then it very much matters. Or if it was 1,000,000 plus -2, it very much matters. But in multiplication, so addition and subtraction, we care about the relative size. But in multiplication, we don't. So just because the bigger number is positive and the smaller number is negative, that has no bearing on the sign of the answer. Also note that kind of a notational consideration is that -1 times a, which we could write as just -1a, that just symbolizes the opposite of a. So quite often, or I shouldn't even say quite often, it's really proper syntax to not write something like -1a or 1a, but just to always convert that to just -a. So if we have a coefficient of 1, the really proper syntax is just to drop that coefficient. So if I had, for instance, an expression like 3 minus 1a, well, this 1a is multiplication, right? I definitely don't want to make this 2a. I definitely don't want to do the subtraction before the multiplication. That would be not in line with order of operations. But I wouldn't want to leave it like this either. I just note that, okay, 1a is just a. I would just write this as 3 minus a. All right, let's do a couple of examples here. So we'll just look at multiplying these integers together. -3 times 9. We're going to move away from our counters now and use this more abstract rule that we kind of developed by generalizing what we learned from our counters. I see I have the product of two integers. One is negative, one is positive. They have different signs. Their product is negative. So the answer is going to be negative. And then what's 9 times 3? 27. So the sign of the answer is negative because my two factors have opposite signs. And the size of my answer is 27 because 9 times 3, if I just make them both positive, that multiplication gives me 27. If I have -10 times -6, my answer, well, these two integers have the same sign, my answer is going to be positive. So I could write positive, but I probably don't want that plus sign sticking around. I just remember that my answer is going to be positive. And 10 times 6 is 60. Negative times negative gives me positive, or the product has the product of these two factors, they both have the same sign. Their product is positive. -1 times 12. Well, -1 times 12 is just the opposite of 12, where that's just -12. That was our just our statement here. -1 times -1. I can think of this actually a couple of different ways. I could think of it as the product of two integers with the same sign, so the answer is going to be positive, and the size of the answer is going to be 1 times 1 or 1, or I could think of it as the opposite of -1, which is +1. Either way I choose to think about it, this kind of fits into both of these rules. Either way I choose to think about it, I get the same answer, +1. Also, of course, 0 is an integer. The integers are the positive whole numbers, like the natural numbers, 1, 2, 3, etc. the negative natural numbers, -1, -2, -3, and also 0, what happens if I multiply by 0? Well, it actually doesn't matter, right? 0 isn't really positive, it's not really negative, just anything times 0 is 0. So 0 is a bit of a special case, but we know from previous work that any number times 0 equals 0. So we apply that previous work to this problem, and that holds for integers as well. We talked about it in the context of whole numbers or natural numbers, but that generalizes to integers. Any number, any integer times 0 gives me 0. Any questions so far? So I think it's a little bit interesting that in, at least from my point of view, um, in the first chapter or so, when we were talking about multiplication and all that, and addition and subtraction were kind of the easier operations, and multiplication and division were kind of the harder operations. Just the process of doing the multiplications and divisions and so on were a little more difficult, I think, most of the time anyway. But in integers, now that we've kind of got that under our belt, for integers, I think it's actually a little easier to do multiplication of integers because we have a much simpler rule to follow than if we were doing like subtraction of integers, right? Like we have to worry about which one has the bigger size, if we were adding integers, like were we adding integers of the same sign or different signs, and then which sign goes with the bigger sized integer, and do we switch the order, and all these kind of things, right? So addition and subtraction of integers, I think, is actually a little trickier than multiplication division of integers. And that might also be signified by multiplication and division both being in a single section and addition and subtraction being broken out to two sections. Okay, what if we divide integers? We have an analogous sign rule for quotients of integers for dividing integers. The quotient, or if we divide two integers with the same sign, we get a positive answer. And if we divide two integers with different signs, we get a negative answer. It's exactly the same rule as for the product of two integers. If we take the product of two integers with the same sign, whether both are positive or both are negative, we get a positive answer. The product of two integers with different signs, whether it's negative times positive or positive times negative, doesn't matter, we get a negative answer. And the same thing goes for quotients for divisions of integers. Again, just like before, the relative size of the numbers does not matter. 2 million divided by -2 is -1 million. It doesn't matter that the 2 million is a much bigger number than the -2. The size doesn't matter. It's just we have different signs. The answer is negative. Okay, so let's look at these three division problems. I have 35 divided by -7. I have the quotient of two numbers, two integers, with different signs. The answer is going to be negative. What's the size of the answer going to be? 35 divided by 7 is 5, because 7 times 5 is 35. So -5. I get the sign by this rule, and I get the size of the number that goes next to the sign, by just dividing the numbers as though they were both positive. -84 over -6, I know the answer is going to be positive. Well, instead of writing a plus there, which can maybe get a little confusing, I'm just not going to write a sign. I just remember that it's going to be a positive answer. And then 84 over 6, well, that might be a little difficult, but I can do long division. 6 goes into 8 one time, 1/6 of 6. 2 left over. 6 goes into 24 4 times. 0 remainder. Looks like 14 times 6 should be 84. So therefore, negative 84 over negative 6 gives me positive because I'm taking the quotient of two integers with the same sign, both negative. So my answer is positive, and its value is 14. Or if I have something like 627 divided by -1, I have the quotient of two numbers with opposite signs. One is positive, one's negative. My answer is going to be negative. The size of my answer, the number that goes next to the negative sign, is going to be 627 divided by 1, or just 627. Any questions so far? So if we're comfortable with doing whole number multiplication and division, really all that integers do is just add in this one extra sign rule. That if the product or quotient of two integers with the same sign, or if the product or quotient, if the problem is a product or quotient of two integers with the same sign, the answer is positive. And if the problem has a product or quotient of two integers with different signs, the answer is negative. But other than this one sign rule, there's not a whole lot that's really new in this expansion to the integers, in this inclusion of negative numbers. So multiplication division works basically the same as it did before, just making sure that we have the correct sign on our answer. Addition and subtraction actually worked fairly differently than they did before. Okay, what if we want to simplify some problems, some expressions? What if I have something like this? Well, again, remember, we do parentheses, then exponents, then multiplication division left to right, then addition and subtraction left to right. Do I have parentheses? Yes, I do. I have two sets of parentheses. Let me simplify each of those first. 6 minus 11, well, the number being subtracted is bigger than the number subtracting from, so the answer is going to be negative. And it's going to be negative of 11 minus 6, or negative 5. And that's multiplied by 8 minus 13, which again is going to be negative 5. So I've simplified my parentheses. I've got negative 5 times negative 5. I have the product of two integers now. There's no more parentheses. Well, there are parentheses just kind of cordoning things off for syntax, but there's nothing, there are no more parentheses that I can simplify the inside of. Negative 5 is just what it is. There are no exponents. I do see a multiplication, negative 5 times negative 5. The product of two integers both have the same sign, so the answer is positive, but I'm not going to write the plus sign. And the size of the answer is 5 times 5, or 25. Okay, if I come down to this next problem, let me erase my little marks up here. Do I have any parentheses? Well, I do have parentheses, but none of them are really acting like grouping symbols. None of them are, none of my parentheses have operations that can be done inside of them. They're just kind of cordoning off negative numbers. They're just making it clear that, if I wrote 52 over negative 4 plus a negative 32 over negative 8, that's like a lot of symbols smashing up against one another. We're not really sure how to parse this, right? It makes the syntax confusing, the kind of grammar confusing. It's a little bit like writing a paragraph with no capital letters or punctuation at all. It's like, I mean, maybe you could really look hard at it and figure out what it means, but it's certainly not easy. So why are these parentheses here? It's not to change the order of operations. It's not to put some, addition or subtraction to give it priority over multiplication like they did up here. They're just to cordon off negative numbers. So we don't have any parentheses that we would want to simplify. There are no exponents to be found anywhere. Multiplication division. Well, I do have two divisions. I have one here. I have one here. Let me do those first. I'm going to be careful to do those before the addition in the middle here. So this 52 divided by -4 is one term. This -32 divided by -8 is another term, and they are being added together. I'm going to do the divisions first. So 52 divided by -4, I have a quotient of two integers. They have different signs. The answer is going to be negative. And what's 52 over 4? We could do long division. You might also know that a deck of cards has 52 cards. There are 4 suits. Each suit of cards has 13 cards in it. So ace through 10, jack, queen, and king. So you can use little tricks like that too if you recognize something like that. But I get -13 for this first, kind of covered that up there, for this first quotient. -32 over -8, I know that I now have the quotient of two integers with the same sign. The answer is going to be positive. And the number that's associated with the answer is going to be 32 over 8, or 4, because 4 times 8 is 32. Okay, now I have the sum of two integers. I have a negative number plus a positive number. The negative number is bigger in size. 13 is a bigger number than 4. I'm adding integers, so now I do care about relative size. Multiplying, dividing, I don't, but adding I do. Since the sign associated with the bigger of the numbers is negative, the answer is going to be negative, and it's going to be negative of 13 minus 4, or oops, -9. So all of this simplifies down to -9. Let me write this again. Okay, next one. Any questions so far? Okay, so next one, -8 times -6 divided by -4. Lots of negatives, lots of stuff going on here. But I start off by asking, okay, are there any parentheses? Well, no parentheses that I can simplify, right? The parentheses that are there are just cordoning off the negative numbers. No exponents anywhere. I do have multiplication division, and I do that left to right. So I have a multiplication here and a division there. I'm going to do my multiplication first because it is the leftmost operation at this level. So I do -8 times -6. I have the product of two integers that have the same sign, both are negative. My answer is going to be positive, but again, I just not write the plus. And the size of my answer is going to be 8 times 6, 6 times 8, 48. And then all the rest of this just copies down, divided by -4. I now have the quotient of two integers, still in the multiplication division level. And I only have one operation left, so I just do 48 divided by -4. I have the quotient of two integers. The signs are different. The answer is going to be negative. And the number that goes with the answer is going to be 48 divided by 4, or 12. We might kind of recognize that 12 times 4 is 48, but that's a little bit outside of the times table. So we could always do long division, 48 divided by 4, and come up with 12 that way also. Or maybe we recognize that 4 times 10 is 40, and that gets us pretty close to 48. Then we could just think, okay, 4 times 11 is 44, and 4 times 12 is 48. Get it by a little bit of guessing and checking. A lot of ways we can get that answer of 12. Okay, let's look at -4 in parentheses squared. So the parentheses are cordoning off -4, and then the exponent comes next. What does -4 in parentheses squared mean? It means really -4, -4 times -4. So this is really the product of two integers with the same sign. So the result is going to be positive. 4 times 4 is 16. I have to be a little careful though, because if I look at this next one, -4 squared without the parentheses, what is this? This is kind of like -1 times 4 squared, right? Right, because we had, where was it up here? Here, right? -a equals -1 times a, or -4 squared is like -1 times 4 squared. Do I have any parentheses that I need to simplify the inside of? No. Do I have any exponents? Yes. Let me do those next. Well, the exponent that I have is 4 squared. Write it below. The exponent that I have is 4 squared. So this is -1 times, I'm not doing the multiplication yet. 4 squared is 16. Any exponents left over? Nope. No exponents now. Do I have multiplication or division? Well, -1 times 16 is just the opposite of 16. It's -16. Be really careful to go through the details of order of operations carefully, right? It's very easy to look at this and say, oh, that's positive 16 because it's -4 times -4. But really, this -4 squared, that's saying the opposite of 4 squared. It's -1 times 4 squared, where this -4 all squared is saying take the opposite of 4, then square that. Or in other words, it's saying take the opposite of 4, multiply it by the opposite of 4, versus take the opposite of 4 times 4. One is positive 16, one is -16. Really easy to make that mistake. Any questions on any of this so far? Questions on anything in multiplication or division of integers? So section 3.4 actually went pretty quickly, right? Like, this does rely on the fact that we've covered multiplication and division of natural numbers or whole numbers before. So we are kind of building off of that, right? If you have a weak foundation in that, then 3.4 is going to be difficult. But if you strengthen that foundation, if you're good at the times tables, if you've been drilling those for the last few weeks or so, and you're solid on your times tables, if you're good at doing multiplication of positive numbers and long division with positive numbers and so on, then 3.4 is going to be a breeze. If you were struggling with that material, then 3.4 is going to be a struggle because now you've got one more thing to think about, right? So ideally, we want to master a topic before moving on to something that builds on it. So if you're looking at this and thinking this is really difficult, then maybe, especially in preparation for the exam, go back to chapter 1 and ask, well, is the chapter 1 foundational material the thing that's giving you the problem, or is it the new material? Sometimes if the foundation is a little weak, then the new material building on it can seem a lot more complicated than it really needs to be. Okay, and then the last topic in chapter 3, solving equations using integers using the division property. So we'll start by modeling the division property of equality. So before we did something, just kind of recall. we might have had something like x plus 3 equals 12. So I would think that I have kind of, two sides here, or two sides to a scale that I want to balance. I have 12 units on the right side, and I have my envelope here, which I don't know how many counters are in. I say that there are X counters in there. I just give it a name, a variable name. I'm not really sure what X is. And I have 3 extra counters on the left side from the plus 3. I can go ahead and remove 1, 2, 3 counters from both sides. My scale should still balance. If I take, 1 ounce off both sides or 3 ounces off both sides, my scale still balances. And now I can just count. I know that my envelope, the contents of my envelope balance with 12 counters. Or sorry, 9 counters. I got to have X equals 9. So my goal is to isolate a single envelope, to get a single envelope by itself. So what can I do over here? I guess there's maybe a couple different ways I can think about this, but I can imagine, okay, if I have 3 envelopes that contain the total number of counters that are represented on the right side here, 3 times X equals 12, I could kind of split these counters on the right side into 3 equal sized groups. If I have 3 equal sized groups of counters on the right hand side and 3 envelopes where each envelope contains the same number of counters as any other envelope on the left hand side, then I should be able to say get rid of 1 group of counters and 1 envelope, or get rid of a second group of counters and a second envelope. Right? I should be able to divide the number of envelopes I have in 3 and divide the number of counters in 3. Or maybe another way that I can think of it is I could have my 1 scale with 12 counters on one side and 3 envelopes on the other side. If I brought over 2 more scales with nothing on either side, I should be able to move 1 envelope and 4 counters to the second scale and an envelope and 4 counters to the third scale, and all of my scales should individually balance now. So I see that I have 1 envelope, oops, has to be associated with 4 counters. So X should be 4. If I substitute that back in and check, does that work? Is it true that 3 times 4 equals 12? Yes, that's a true statement. I'm now confident that X equals 4 is my solution. Each envelope has 4 counters in it. If I have a situation like this, again, I have 3 envelopes. So I'll start splitting these counters up in groups of 3, or sorry, in 3 groups. So I see that I can do 2, another 2, and another 2. So I can kind of like assign 1 group of 2 to 1 envelope, a second group of 2 to a second envelope, and a third group of 2 to a third envelope. And I can kind of make this assignment to make it clear what's happening. I have 3x equals 6. This says x equals 2. Each envelope has to be associated with 2 counters. And as usual, if we had 20 envelopes and 100 counters, I wouldn't want to draw those all out and start circling a bunch of things. So we do this modeling to try to get a bit of an intuitive understanding. And then we try to generalize away from the model with counters and envelopes and green and red counters and all of that. So solving equations using the division property of equality, if A equals B, and if we have a third number C that's non-zero, then A over C equals B over C. And this is true for A, B, and C integers. It's also true for fractions or real numbers, but at the very least, we have this for integers. So if I look at an equation like 3 times x equals 6, I have kind of like A equals B. I know that I can divide both sides by the same number as long as it's not 0. I don't want to divide by 0. I can divide both sides by the same number and still have a valid equation. My resulting equation after that operation, dividing both sides by the same number, will have the same solution as the original equation. Now I look over here and I kind of think that if I have one scale with 3 envelopes and 6 counters, it would be nice if I had 3 scales, each of which having one envelope on one side and who knows how many counters on the other side for each, and then make it balance. I would like to divide this left-hand side with 3 envelopes into 3 scales. I want to divide by 3. Can I divide by a number that's not 0? Yeah, sure. So I have 3x divided by 3 is equal to 6 divided by 3 by our division property of equality. But really, this is just 3 times x divided by 3. And on the right-hand side, I have 6 divided by 3. If I have 3 times x divided by 3, that's just x, right? If I say I have 3 envelopes and then I split them into 3 groups, each group just has 1 envelope. Right? If I had 3 counters and if I had 3 pieces of candy and I split them into 3 different bags for 3 different kids, each bag gets 1 piece of candy. So 3 of these things divided in 3 parts just gives me 1 thing in each. So I just have x equals, and then what is 6 divided by 3? Well, that's just a basic division problem, right? That's just an arithmetic operation that we now know how to do. 6 over 3 is 2. So I can get my same answer, but I didn't have to draw out counters and envelopes and all of that. I can get it more abstractly. If I have bigger numbers that are more annoying to work with, I can use all of the arithmetic techniques that I've built up, long division and how to do multiplication or addition, subtraction. I can use all of that, bring all of that to bear on this problem on this right-hand side. So if I want to solve 4p equals 64, again, my goal is to get p equals something. I want this p by itself. Or I kind of want to split those like 4 envelopes. I want to split them into 4 pieces so that I'm just looking at 1 envelope. Can I divide both sides by 4? Yeah, sure. On the left side, 4p over 4 is just p. And on the right side, I have 64 over 4. That turns out to be 16. Now, again, I could, if I didn't see right away that was 16, no problem. I could go over and do long division, or I could do a little bit of guess and check. 4 times 10 is 40. We need a little more than that, and so on. What if I want to solve something like this? Negative 9x equals 54. It's a little difficult to model this. I mean, we would need red counters or like red envelopes like that would have counters that we like take away or something. But yeah, exactly. We have to divide. We can use our same abstract strategy here and just say, well, what have I been doing? I've taken the coefficient of the variable, I've taken the number multiplying the variable, and just divided both sides by it. Can I do that here? Sure, I can divide both sides by -9. So we can think of this as -9 times x divided by -9 equals 54 divided by -9. Make sure to do the same thing to both sides. And exactly, yeah. As Raj says, on the left, we just get x itself. Now, like, if I take -9x and split it into like -9 parts, does that model generalize very nicely? Not really. It's kind of complicated to think about. But does the mathematics generalize? Sure. Yeah, this works for any number C that's not zero, even if it's a negative number, even if it's a little hard for us to visualize, like having bags that when I put something positive into the bag, it means take it away. Or if I think of, you know, um, kind of assets versus debts or something, it's going to get more complicated in our model, but we can use this more abstract representation of things and just kind of follow it instead of our models with whatever application we might want to use, counters or real line or candies into bags or whatever. And 9 times what is 54? Well, 9 times 6 is 54. And I have the quotient of two integers with different signs. So the answer is negative. That's what my sign rule for quotient says. Quotient of two integers, different signs, answer is negative. So x equals -6, or I can imagine that I have like 6 red counters in each envelope. And each envelope is saying, each of these 9 envelopes is saying, take away the counters that are inside. So I'm like taking away 6 red counters 9 times. That's where I get the positive 54. Or right, I can check, is -9 times -6 equal to 54? Yes, it is. So I've checked that this is indeed a valid answer. If I want to solve, say, -8m equals -40, again, it's a little hard to think of like uh, envelopes that mean take away or red counters versus green counters. A lot of complexity here, a lot of moving parts, but I can, again, just follow my property, follow my general strategy that I've been doing. I have a coefficient of the variable. That coefficient is -8, the number multiplying the variable. I just divide by -8 on both sides. Oops. On the left side, I'm just left with m. And on the right side, I have the quotient of two integers. They have the same sign, both are negative, so my answer is going to be positive. But again, just as a matter of convention, I'm not going to write the positive sign. And 40 over 8 is 5 because 5 times 8 is 40. Right? If I lean on the property instead of the model helps me understand things at an intuitive level. But once things get complicated enough, I don't really want to keep coming back to the model. I want to lean on the property, the generalization, the abstraction from that model. What if I have something like this? -75 equals 15 times y. If I was following my nose a little too closely, I might try to divide by -75. But remember, what was the idea? The idea is get the variable by itself. So I want to divide by the number that's multiplying the variable. In this case, I want to divide by 15. Doesn't matter which one's on the left or the right. It's which one's attached to the variable that matters. On the right side, I'm just left with y. On the left side, what do I have? Well, I have the quotient of two integers. They have different signs. My sign rule for quotients says the answer is going to be negative, and 75 divided by 15 is 5. Oh, and we're making great time through all of this. Um, any questions so far? Okay, now let's look at two more examples here. Let's try to solve 4 times u equals 0. Let's solve it algebraically and then look at the model. We will actually go back to the model for this one to kind of see what's happening. What's my strategy? I divide by the coefficient of the variable. So I'm going to divide by 4. Yep. 4u divided by 4 is just u. And 0 divided by 4, if I have no candy bars, and I have 4 bags to distribute them to, how many candy bars go in each bag? 0. Or what am I saying? I have my setup over here with my 4 poorly drawn envelopes. And how many counters on the right side? Well, actually 0 counters on the right side, nothing on the right side. This balances how much does each envelope contain? How many counters does each envelope contain? Well, if any of them contain any counters, it would not balance. The left side would be too heavy. These envelopes can only contain 0 counters each. What if I had a similar looking problem, 0u equals 4, and tried to solve it? I might be tempted here to say u equals 0 as well if I was just kind of glancing at this. Does that actually work? What would my solution strategy be? Well, I'd want to divide by the coefficient of the variable. I want to divide by 0, but that's kind of like, frowny face. We don't want to do that. I don't want to have u equals 4 over 0. That would be like saying, I have 4 candy bars. I have 0 bags to put them into. How many candy bars should I put into each bag? That's kind of just a nonsense question, right? There are no bags to put them into. I can't answer the question, how many should I put into each bag? Or what am I saying over here? I'm saying I have 4 counters on the right side. How many envelopes do I have? Do I have, 3 envelopes? No. Do I have 2 envelopes? No. Do I have not even 1 envelope? I have 0 envelopes. How many counters are in each envelope? Well, first of all, that's kind of a silly question because there are no envelopes. But we can actually see if there's no envelopes on the left side, how is this ever going to balance? This is just always 0 weight, and this is like 4 units of weight. It's never going to balance. In fact, if I think of u as being an integer, I know that any integer times 0 is 0. This really just simplifies down to 0 equals 4 if I notice that. And 0 never equals 4. This is a false statement. It's a contradiction. There's no u, no value for u that solves this equation. So I need to be a little careful, right? I have to really take to heart this restriction that c cannot be 0. If I just kind of flippantly try to divide by 0, I mean, hopefully I would get to 4 over 0 and realize, oh, okay, wait, something went wrong. I divided by 0. But I might, if I was being a little too fast and loose with things, I might do 4 over 0 and think that that's 0. 0 over 4 is 0. That's perfectly fine. There's nothing wrong with this previous example. We just had 0 candy to distribute to 4 bags. Nobody gets any candy, sorry. But if I have 4 bars of candy to distribute to 0 bags, how many go in each bag? That's kind of a nonsense question. So this would be no solution. Are there any questions on anything from today? So we actually covered quite a bit of material today. Both sections 3, 4, and 3, 5, wrapping up chapter 3. Oh, it was fun. Well, I'm really glad that you enjoyed it. Hopefully I know one of the big uh, conceptual difficulties folks have is like, why is a negative times a negative a positive? They can say, okay, I can apply the rule. If you tell me negative times negative is positive, I can do it 10 times on a homework set. But like, why should that be true? And hopefully this model gave you a little bit of an answer as to why it should be true intuitively. Either we're kind of like facing to the left and then walking backwards. So net, we're kind of moving in the positive direction. Or we're like taking away counters of what kind of the red kind, leaving us with extra greens. So hopefully that gives you an intuitive answer to that, but also the rule to rely on in general so that we don't always have to draw a whole bunch of counters or, little folks on a number line or something. And we're building up to being able to solve equations by actually kind of combining these two properties. We now know how to solve like x plus a equals b types of equations, and we know how to solve ax equals b equations. What about like ax plus b equals c? We're building up to solving equations like this, and really to being able to solve really any what we would call linear equation. So even something like ax plus b equals cx plus d looks really complicated, but at this point, we basically have all of the tools that we need to solve such an equation. We just need to put them together in a little bit of a different order. We need to be careful about the order we put them together in, but we've got all of the tools created, so to speak, with our different equation properties. Okay, any questions on anything from today?